Anyway, well, hi, yes. So problem 13, it's a juicy one. I really like this one. I like this so much that there's one just like it on the quiz. Isn't that exciting? So where do we start? Current path, 80 joules of heat leaves the system. And that means 80 goes here, but since it leaves the system, I want to put a minus sign in it. And 55 joules of work is done on the system. Now, done on is supposed to be code word for negative. But since you have a diagram, I keep stressing this, the best way to tell whether the work is plus or minus is to look at the direction of the arrow. So the delta V is getting smaller. Not smaller, but the delta V is negative. So that means that that number has to be negative.
When they use the phrase done on, does that always mean negative, or do you have to look at the picture to tell?
Yeah, done on does mean negative, right? So another way to think about that, and I'm recognizing the fact that that is very confusing. So another way to think about that is because we have the system and something from the outside world is forcing work upon it, that the net effect is going to be to increase the amount of energy available to the system. And so when we look at delta U as Q minus W and W is negative, then that does in fact mean that the energy of the overall system is going to increase. And here's another way to think. I don't know if this is going to work for you, but another metaphor, if we turn around and go the other way, when the gas expands, and just think if you're like working out in the gym or something, and you push against some static weight, when you expand, that's why it's a workout. So the work leaves the system and it's not available anymore. All right, now having said that, we do 80 minus a negative 55, and so that should be negative 25. Now you have reactions down there in the bottom. It would be nice if you could just give me like a hand wave or a thumbs up if that sounds good to you. Yeah, great. Okay, so what else do we know? Well, we can build on this. So that's delta U going from A to C. And this has the same endpoints. This is also A to C, going the same direction. It doesn't take the same path, so all the pieces parts will be different, but it has the same endpoints. So this is also negative. And then when we go down here, this is C to D to A. So that also has the same endpoints, but reversed. So it'll still be 25, but it'll be plus 25. Gonna see a hand clap for that. Okay. Thanks, Beth. The rest of you, I won't take that personally, but try to stay with us. All right. So what's next? Well, there are a couple of easy ones, right? So work done from D to A, that's 0. So you can put a big fat 0 in there. And B to C, the work done is 0. So I can do that. And then what are some other things that we know? Okay, when we go CDA, so that's this number down here, it says the work done is 38. And that checks out as being positive because it's an expansion. The delta V is greater than 0. So that should be positive. And therefore that makes this, because C to D and D to A should be 38. So this is also 38. So I know that to be true. This clue right here, A to B, the change in internal energy is 10. So when we do deltas, we always do final minus initial. So even though it says UA minus UB, it's actually the change in internal energy when going from B to A, because A is the final state. But here we want the change in internal energy going from A to B. So that's opposite. That's going to be negative 10. Just want to pause. Just let me know if you want me to go through that again. Thanks, Anna. All right. Good. So now I know that this delta U plus this delta U has to be this delta U. So that makes this negative 15. And then since I know two things on this row, I can come over here and put in the Q. So that's going to be negative 15 also. Well, now I know two things on this row, so I can figure out the third one here. So I need a number so that when I subtract 38 from it, I get 25. And that number is 63. 63 minus 38 is 25. But after that, I'm kind of stuck in this last group here. I really don't have enough information to find anything else. So to let that sit. And then the last part is this clue right here. You remember we saw this one, and we saw a clue like this for problem 12 that we did last time. And it says that the pressure is 2.5 times greater than the pressure at D. So the pressure at C is the same as the pressure at D because it's isobaric. And when we calculate work done here, we go pressure times change in volume. Now the change in volume is the same up here going from A to B. It's the same as opposite, it's a negative number, but in magnitude it's the same. It's going to be the same number. And the pressure is just 2.5 times greater. So when we do pressure times change in volume, if the pressure is 2.5 times greater, then the work done will be 2.5 times greater than this number, than 38. So we can just multiply that, multiply 2.5 times 38. And that is 95. But we also have to remember it's a contraction. So it's and then that means that this has to be negative 95. And if we go
Sorry,
up here,
can you just repeat that?
yeah, absolutely, sure.
How you're getting.
So let me do this. 2.5 times 38. Minus 10. So since the change in volume is the same, the length of these arrows is the same, but this arrow, this path is 2.5 times higher. Remember, area under the curve is just all this stuff, right? So if I was to draw a little rectangle here, the area of that rectangle would be 38. But then this is 2.5 times taller, so the area of all this stuff is going to be 2.5 times greater. So that's why I multiplied by 2.5 to get 95. A little bit better?
Can you repeat that?
Yeah, let's try and do it in a different way. Let's see.
Please.
Let me go down to the bottom of this. Okay, so let's just add in a little workspace. We can actually, you can see the math. Right? Okay. So, work done in going from C to B equals 38. That has to equal pressure at B times the change in volume. So I'm not going to take the time to look up what delta looks like on this particular piece of software, but Should be able to. Well, anyway, let's pretend. Yeah, well, that did work. Okay, good. And now I'm just going to copy and paste that. And then we want to do the work done from A to B. So this is going to be equal to the pressure at B times negative delta V, because the change of volume is opposite. And so that would be equal to, well, the pressure at D is 2.5 times greater than the pressure at D. So this is 2.5 times pressure at D. So I just did a substitution. And so that means that the work done is going to be equal to negative 2.5 times 3, and equals negative 95. How about that? Okay, the protests have died down. So I think we've beaten that one adequately. Now it's time to actually check answers, which is kind of exciting because let's go up here. I know two things across the top. So I'm looking for a number so that when I subtract a negative 95, I get negative 10. Or another way of thinking about it is that Q is actually equal to U plus right, so I can actually just add these together, and that's going to be negative 105. And then by the same token, I can just add these two together. So negative 95 plus negative 25 is going to be negative 120. But then you can see that negative 105 and negative 15 add up to negative 120, and so that proves that it works. So we check our answer. Yay. And I can't really go any further. I don't have enough information to do anything else. But let's go ahead and check and see how we're doing with the questions. So what's the change in internal energy going from C to A? And so we got that. It's plus 25. And then how much heat is added to the gas in the process C to D to A? That's 63. So we got that. How much work is done by the gas in the process ABC? That's negative 95. We got that. What's Q for ABC? That's negative 120. We got that. And then if going from B to A is positive 10, what's Q for the process BC? I got that. It's right here. It's negative 15. And there we go. We got it. We answered all the questions. So what was confusing? There were a couple of places. So obviously this little maneuver right here, the 2.5 times 38, that was challenging. Trying to visualize that. And then a couple of other things like recognizing that this delta U is going to be positive, the opposite of these values. And then just in general to be careful because some of the numbers have negative signs and there's a negative in the first law. So we just have to be a little careful. Okay, I'm going to stop sharing and we'll come back and take a look. So just to give you an example of a real life PV diagram, there is an example. I'm going to go back to Canvas. So if you want to follow along with me. Can everybody see Canvas? Beth, thumbs up. Thanks. And here's my agenda. So here's a link right here. And what's the best way to do this? I think I'm just going to follow this link and go out to the actual website. And this is a PV diagram for an internal combustion engine. I'm going to grab this link and I'm going to just pop it into an email for you. And as I said, that's the internal combustion. So please go ahead and check your messages and then open that link really quick. And just going to talk about it really quick. But this too is going to be part of your quiz coming up. And I want to describe the things that you ought to be able to do with it. So I'm going to stop sharing and then make sure I do share the right window. I think it's this one. Nope. Just made a mess. Okay, so I'm taking a look at this diagram right here. This is on my agenda, but you have actually the real source. So the kind of things I would ask you to do are to talk about where is the work positive, where is the work negative, and the abbreviations. You have a key for the abbreviations on the actual website. But we'll take a look at the internal combustion engine in a second. IVO is intake valve open, and EVO is exhaust valve open, and ignition, and then intake valve closed. Actually, I'm going the opposite order, sorry. Exhaust valve closed, intake valve closed, ignition, exhaust valve open, intake valve open, exhaust valve closed, and so on. So you can see this is an example of what happens. And this is the bang right here of a spark plug. And it continues to drive the pressure up. But then as the cylinder expands, then the pressure drops. So we'll take a look and sort of piece this together. So I'm going to have a diagram of the internal combustion engine, and I'm going to have this. I'm going to ask you to make some connections between the two. So I would ask that you read a little bit about what's there. And then we're going to come back to this in a few minutes. But now I want to move off the agenda and start talking about the slides for tonight. Okay. I'm going to stop sharing just so I can find my notes. Sorry, I thought I had this open already. Okay, somebody, I can't see your screens anymore, but if somebody could just unmute and say, yes, I can see the slides.
I am not currently seeing slides. I don't know about anyone else.
Okay, good. Glad I checked.
Yeah, I don't see him either.
Better?
Hey, yes.
Okay, excellent. Here we go. As I mentioned before, it's super abstract, but hopefully that chart helps you understand this first law a little bit better. Because it's an interplay between three variables at the same time, and the easiest way for us to think about it is when one of the variables holds fixed while the others change. Or better yet, if they're zero. So last time we talked about the importance of the PV diagram, because each point on the PV diagram, this is an important conceptual question, each point on the PV diagram also refers to a temperature. And since it refers to a temperature, it also refers to an internal energy. That's a big idea. So a conceptual question might look like this. What's the connection between a point on a PV diagram and temperature? We talked about 4 thermodynamic processes that you should know. Isothermal, where obviously the temperature stays the same, but the other key is that the internal energy stays the same. So delta U is 0. And then adiabatic, and you can't really tell adiabatic and isothermal apart on a PV diagram. You need some additional information, but adiabatic means there's no heat added. And a famous example of no heat added is a snow gun. And then isobaric and isovolumetric, we just were exercising those. For isobaric, the pressures, or the work done is P delta V, and for the isovolumetric, the work done is 0. So you can string these processes together in order to get a cycle. And then I talked about how each one of these steps simplifies the first law. So this roughly, like if you have a Fitbit or a smartwatch on your, that's counting your rings and things like that. So it's based on human metabolism and your heart rate. So you had to do a couple of things of data entry when you set up your phone, and those variables are enough for you to combine with your heart rate to figure out what your metabolism is doing. It's an approximation, but at least it's something. You know, it's better than nothing. And it's not even doing a heart rate. It's I don't think. I think it's just doing your pulse. I don't know. I'm going to find out more about that. All right. Well, anyway, this just gives a range of different activities. And right, so if you're trying to hit your target, it's hard to do it while sleeping, but it's easier to do while you're bicycling or when you're running because you pick things up. Right. So the basic idea is that roughly, in order to get the same workout from walking compared to running, is that you would have to run for a little more than twice as long. All right, so this is a really important slide. This is where it all starts. And the basic idea is that heat flows from a high temperature to a low temperature. If you don't have a temperature difference, heat does not flow. But as soon as you can establish a temperature difference, then heat does flow. So how can you establish a temperature difference? Well, you could set something on fire. That's an easy way to think about it. And if you think about a wood stove, then the high temperature is inside the wood stove and the low temperature is the end of the chimney. So that's the temperature difference we would be talking about. And those temperatures would be in Kelvin. Now, in the process of going from one temperature to the other, heat engines can extract some of this energy in the form of work. And that's based on the first law. So if we don't extract any work, then we just go straight here and the energy gets dumped into the low temperature reservoir. So usually what these things are there sources of high temperature that's large enough that the temperature is not going to drop based on us extracting a little bit of heat. And then this temperature is low enough that it's probably not going to change very much. It's big enough, so it's probably not going to change very much based on the heat we dump into it. Right, so the wood stove, as long as you keep adding wood, the temperature is going to stay the same. And you're losing heat out the chimney, but that heat that goes out the chimney is not really going to heat up the outside world. Not on that scale anyway. And in the process, we can extract out some heat. So with the wood stove, we don't extract out work, we just extract out heat to warm the home. But it is an example of a heat engine. Oh, all the text. All right, so with heat engines, we typically run in cycles, and we want to examine what happens in the exchange between heat and work while we run a cycle. So in this slide, here's an example of a heat engine. In the boiler that makes steam, this is TH. And so QH, this is where we're getting the heat from. But when the steam flows in, it pushes against the cylinder. This is a steam engine. It pushes against that and does useful work. But in the process of doing that work, the steam cools off. So we have hot steam that pushes the cylinder, and then we get cooler steam. But you still have to work really hard to condense that and be able to begin the cycle again. So that's why it's important there's so many power plants that use the same process. This could be a nuclear reactor that heats up the water. And it's the wood chip plant, it's wood chips that are burning that heat up the water. But then you still have this hot water left over that you have to condense in order to repeat the cycle. So and that's why power plants that do this are always next to a large body of water. So the McNeil wood chip plant is taking water in from the Winooski River and dumping it back into the river after they've used it to condense some steam.
You
So
disregard my question. I asked that question in the chat, so.
yeah, okay, good. Sorry, my chat thing disappeared. Oh, what's the question about? Doesn't that heat up the water? Was that your question, Marianne?
I asked if it was similar to the nuclear power plants with the heating and cooling process, but you just.
Yeah, exactly. So, and then again, that's the reason why these power plants have to be next to a river or a lake or something like that, is because they're sucking in water and they're using it to cool off their steam, and then they dump it right back into the lake or the stream. So the question is, does that mean the McNeil wood chip plant heats up the river? And the answer is yes, definitely. And there are, they're supposed to monitor what that additional heat is, and they're supposed to make reports on what that is, because there are regulations on what they can actually do when they're discharging heat into the river. you all know enough chemistry to recognize the fact that the dissolved oxygen content will decrease when the temperature is warmer. So you got these fish swimming upstream and they're like, whoa, is anybody else like getting low on oxygen here? And then once they pass the power plant, they're like, oh, there's lots of oxygen now. So, yeah, there are a lot of unsavory things about where we get our energy from. Just one more thing. So here's an example of a different kind of turbine. So this could be connected to a generator, and the turbine cranks around, turns the generator, and generates electricity. So high pressure comes in, but this high pressure steam winds up at a lower pressure steam, but it's still steam, and it's got to be exhausted to a condenser in order to repeat this cycle again. But this is an example of how we're pulling off some of the thermal energy because we're asking it to do work. Here's the internal combustion engine. So what does that look like? Where's the Q? Where's the exhaust? Where's the TH? Where's the TL? So let's check the number of strokes that this goes through. So we start off, we have a downstroke here, and the piston is expanding. And the intake valve opens and allows fuel to enter. And the expanding piston helps draw it in. So in older vehicles, we had something called a carburetor that would mix the fuel and air together, and then this would draw in the air from the carburetor. But these days, most of the engines are fuel injection. So it just gets squirted just right in there. And it's a little more efficient because instead of the timing being mechanical, it's electronic. And it can be tweaked a little bit to increase efficiency. As this expands, fuel runs in, and then the valve closes. So we have two valves here, intake valve and exhaust valve. And with the valves closed, as the crank comes around and starts compressing this again, in this process, this is an adiabatic process because there's no heat added, but the fuel mixture gets hot quickly. And in fact, in a diesel engine, it gets so hot so quickly that it actually explodes spontaneously. And a gas engine needs a spark plug in order to set this alight, but a diesel engine actually doesn't have spark plugs because the pressures get so high. That's usually why diesel engines are found in much larger vehicles, because the engines typically have to be much larger and sturdier in order to withstand the high pressure that diesel engines work at. And you might say, well, that sounds kind of efficient, you know, bigger engines take more metal and all that. But the reason why they're used is because diesel is the lowest form of oil. It's the sludge. It is the nasty stuff. It's almost the same thing that people burn in their homes. So in the fuel refinement process, crude oil gets refined into gasoline, butane, and then what's left over from the crude oil after you've extracted all those hydrocarbons is just this absolute crap. So there you have it. Bang, spark plug goes off. We have expansion and work is being done. So this is where the QH is. This is where we get the thermal energy from. And then we suck off some work and then we exhaust this out. And this is where the QL is. So by its very nature, anytime you're burning something to run a heat engine, it's never going to be 100% efficient. There's always some loss. So we need a temperature difference, otherwise heat's not going to flow. And now we can talk about efficiencies. So efficiency in general is categorized by how much heat you harvest. Now I use the word harvest, it says QH. It's not a bad connection, although the intention is to call this Q from our hot zone. So we're able to extract some work when we harvest this Q, but then we're going to have some left over. Then we have to ditch. So if efficiency is equal to if W over QH, then we also have to recommend that the work done is simply the difference between the heat that we harvest and the heat we ditch. the heat we waste. Yeah, that's waste. That is waste heat. And it's always the case when you're doing a heat engine. You're always going to have to waste some heat. The only way you don't waste any heat is if the exhaust temperature is absolute zero. So there's always going to be some inefficiency. And so the efficiency, that's what E stands for, is 1 minus, if you will, the inefficiency. So this ratio right here, the amount you waste compared to what you harvest, is another way of measuring inefficiency. So one very special kind of heat engine that is talked about is called a Carnot engine. It's named after a Frenchman, so we don't pronounce the T, so Carnot. And it consists of 4 steps, 2 isotherms, and 2 adiabats. So remember, adiabatic processes and isothermals are hard to tell apart. So if we follow the cycle around, that when we start off from A to B, that's an isothermal expansion. And so going from A to B, so it stays at the same temperature, which means the internal energy doesn't change, but Q gets dumped in, and that's how come the expansion happens. So we dump in QH, that's what we're harvesting. And then by virtue of taking away the heat source and still allowing some expansion to happen, this, if the heat source is gone, then this is going to be an adiabatic expansion. In both cases, there is area under the curve, so work is still being done. But then in the next step, we have an isothermal compression. And so work done here is going to be negative. And heat is exhausted from the machine. Then there's an adiabatic compression, so it continues to compress and gets back to its original state. So the work done is the area under the curve. So we have positive work from A to B and positive work from B to C. But when we go back the other way, it's negative work. But it's happening at a slightly lower level so that there is a gap in between the two. And the gap in between the two represents the work that's actually done by the machine. So we suck Q in here, and then we exhaust Q out. Now, since the Q going in happens along an isotherm, this is a big conceptual idea. Since the Q is happening along an isotherm, that means that there is a direct proportionality between the heat that we obtain and the temperature. So that means for the Carnot engine on its own, by itself, I'm actually going to skip ahead a little bit. For the Carnot engine, we can express the efficiency as a function of their temperatures instead of measuring heat. And that's a little bit easier to do. So we're about to take a look at some examples, some problem solving. But I did want to just go through a couple of slides that I put in here. This is Vermont Yankee down in, is that right, Windsor? And so this is a Google Earth screenshot. And then this is it. This is the reactor building right here. And this is a row of cooling towers. And you can see the steam coming up. That's not stuff burning, it's just steam. And you'll see the same cloud of steam at the McNeil wood chip plant, especially in the winter. So that's what's happening here. You have this the steam that needs to get cooled off. So they pull in water from the river. And, oh, Vernon, that's where this is. So if I switch into presentation mode, you can just see that slide in a little more detail. So Vermont Yankee, this is the only power plant, the only nuke in Vermont, and it has been since decommissioned. So we're not getting any power out of it right now, but it's still hot. So it's going to be hot until for another 53 years. So that means we still need to run. We have to have operators to make sure no accidents happen. We still have to hire security guards that have to watch it 24/7. So there's a considerable expense in decommissioning a nuclear reactor. Right now, the fuel cells that are there are spent, but we don't have any place to put them. So they're just in storage right there on site. Oh, and what's this? Vernon Elementary School. How cute is that? So when you're on your way to work at the nuclear power plant, you could just drop your kids off right next door. Isn't that great? And surprise, it's right next to the mighty Connecticut River. So water is sucked in from the river, run through these cooling towers to cool off the steam before it gets dumped back into the reactor. Thanks, Vermont Yankee, for keeping our rivers warm. So here's a rough idea at what's happening inside the core. That we've got the reactor, and these black lines are supposed to represent control rods. So later we'll talk about the exact mechanism for how uranium-235 is undergoing a chain reaction here. But the control rods can be used to moderate what the power output for the power plant is. At full power, it was 620 megawatts, and actually, my best friend was arrested when it went online back in 1972. There was a lot of protesting going on, not in my backyard. To give you a comparison, the McNeil Woodchip plant is about 80 megawatts. So there's a lot of power coming off the nuclear plants, and the grid really likes the nuclear plants because they provide a nice solid background hum of electricity, and all the renewables sort of sit on top of that and get managed. And 32% efficient, which actually is remarkably high for burning stuff. Right. Okay. So again, we have cooler water that is pumped into the reactor, and then it gets heated up. And then the heated water goes off to a turbine, spins the turbine, but then that steam has to get cooled off and then eventually gets cycled back. So that's it. This part is happening inside the reactor building right here. It is relatively clean, except for the byproduct of the spent fuel rods, which is among the most deadly material known to humans. And then here are these cooling towers. But wait, what happened? Oops. So 13 years ago, one of the cooling towers just kind of collapsed because it was made out of wood, and there were some termites in there. Yay. Yeah, so it had to be taken offline for a little while. Anyway, back we go to the efficiency for our Carnot engine. So the big deal is if you're working on something that says Carnot heat engine, then you don't need to use the Q's to find the efficiency. You can use the temperatures. I'm going to skip out presentation mode here and then come back to this idea. We can actually run this process backward. So you can put work in and then drive heat the other way. So a refrigerator and air conditioner works like this. You can extract heat from a place that you want to keep cold, and then you can dump it into a place where you don't really care that the heat goes. So on a hot summer day, this would be the outside, and then this would be the inside, like a bedroom or something like that. And so you're extracting heat and then you're dumping it outside. I've heard stories. Burlington is famous for having this beautiful, majestic homes chopped up into as many apartments as they can possibly do. And sometimes you'll have folks that have a window between bedrooms. Right? How did that happen? My first apartment in Burlington, I got the short stick. I got the bedroom that was a converted porch with no heat. So, word to the wise, if you should have an apartment like that, don't put an air conditioner inside that window because it might make your room cold, but it's just going to make the other person's room really hot. All right, and here's what it looks like on the back end. So we have a bunch of coils in the back end. And this is where the QH gets, where the QL gets dumped. So you have a compressor, that's what's doing the work, and it's compressing these gases and then allow it to expand really quickly, kind of like a snow gun. And so then this vapor is really cool. It's much colder than the temperature of the air inside the refrigerator. And so as the coolant winds its way through the cooling elements of the refrigerator, it soaks up heat from the inside, and then it comes out the back. So an expansion valve is just a needle nose hole in a pipe obstruction, and that allows the air to expand and now dish their acquired heat into the outside world. You can do this with a mechanical pump. When I was in the Peace Corps, I actually had a kerosene refrigerator. And so instead of a pump, I had a jug of kerosene with a wick. I would light my refrigerator. And then, boy, my neighbor, I was really popular because that was the only place in town to keep the beer cold. Okay, well, we don't have to worry about this too much, the coefficient of performance, but just a reminder, this is a really sought after heating mechanism to use the fact that once you get about 4 feet deep here in Vermont, that's the frost line, and below there it stays right around 55 degrees all year round. So you could actually extract heat from the ground, use it to warm your house, or you could extract heat from the ground and use it to cool your house. So this is called geothermal heating. It's expensive, but it's highly efficient and costs very little. Okay, well, let's do some practice problems really quick. We've been on it for about an hour, but we don't, I'm going to forego the break if you don't mind, because we don't have very much left to do tonight. So here's our agenda if you want to take a screenshot of it. And I'll be writing down some of the specifics on the board. Okay, just pause it really quick. Anything you want me to double back on? I said a couple of, this is an important conceptual moment, and that means those are usually going to show up as conceptual questions on the quiz. Okay, so these are 4 quick examples. If you've been doing screenshots, then that's 3 of them, and then this is the 4th. I'll upload this agenda. I thought I did, but I'll make sure that it's lives up on Canvas so that you can download it, because I also have answers to these as well. Okay, well, here we go. I'm going to stop sharing and then change my screen and then use the whiteboard. Whose head is that? This is 18 of the problems that are listed in Canvas. I hope to be migrating over to Mastering Physics next week. So we have a heat engine that does 9,200 joules worth of work. So work equals 9,200 joules. Is that standing up well enough? Jameson, what do you think? Thumbs up? We got it? Can you see what I'm doing on the board all right?
Yeah, that's pretty good. Can we, no, I think that's as far as your resolution goes. So yes.
Let me double check the focus. Is that any better? Do you want me to zoom in more?
Zoomed in a little more would be nice. Trying to get that creme de la creme webcam shot. Yeah, there you go.
Okay, good.
Nice.
And then QH equals 22 kcals. Okay, so that's just annoying because we have to convert that, of course. And so here's a quick reminder. Obviously, you can use the internet to convert it if you want. But we know that a kcal is 1,000 calories. And if it was just a calorie, that's the heat required to heat up 1 gram of water by 1 degree Celsius. But it's 4.186 joules to do the same thing. So if this is kcals, then we're going to write it as 4,186 joules per 1 kcal. And so I get 92,092 joules. And the question is, what's QH and what's the efficiency of this engine? So again, I'd like to just come back to that diagram again. So we harvest QH and suck off some of it to do useful work, and then the rest of it just gets wasted. I know, it's so depressing. This is thousands and thousands of years we've been doing this, and just burning stuff and just dumping heat into the atmosphere. All right, so in terms of numbers, then what we have sucked off is that this was 92,092 joules. And then what we got out of it was only 9,200, like a tenth. And that's par for the course. So this is actually the difference between the two. So I'm going to go ahead and just subtract that. It wasn't really asked the question, but I think it helps illustrate what's going on. So after harvesting this much heat, we're going to waste 82,892. Now, a little side note, because we're going to probably see examples like this. If this is a continuous cycle, I mean, it looks like this is a one-shot process, right? So if this was actually something that continues, one of the things that you're likely to see is something like this. That many joules per second, that many joules per second, that many joules per second. And then this, instead of just being work done in a finite unit, would be power output for this engine. So I'm just bringing that up, that you can do this process with energy, or you can also do it interchangeably with power. Harvesting power from a hot zone, subtracting off and getting some useful power out, and then exhausting power into a low temperature heat sink. All right, now as we take a look at it, the efficiency is the ratio between these two. And so E is equal to work over QH, like what we got out of it compared to what we harvested. Right, so for sweet corn, right, this is the corn we got out of it. And then this is the actual ear of corn. And then QL is the husks and the leaves and all that stuff. So that's one way to write it. And then you can also do it like this, which is 1 minus the waste amount, which is QL to QH. All right, so here's what we get for a number. So it's 9.9% efficient. Good Lord. And on the bright side, this is the same thing as 1 minus 0.90. So you can clap and offer up some applause that this particular process is 10% efficient, or you could say it's 90% inefficient. Huzzah! Burning, 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 always burning. All right. Any questions? Actually, so now we're getting to, compared to what we started off tonight with that big thermal chart, this stuff is actually pretty easy. But if you get confused, always come back to this chart, because that helps keep you organized, because you have lots of Q's and W's floating around. So remember, we harvest, we use, and then we waste. So let's take a look at Carnot problem really quickly. And so that's number 20 of the homework. So now we have a TH. Problem 20. We have a TH, and then we're going to extract out energy, and we're going to dump into TL. So TH is where the Q comes from. Right, so this temperature could be the temperature on the inside cylinder of an internal combustion engine, or it could be the temperature inside a wood stove. And then this is where the exhaust happens. And then we get work done. But since the QH, this is for a Carnot cycle. The QH happens on an isotherm. So that means QH is proportional to TH. And likewise, QL, because QL happens on isotherm, is proportional to TL. I think there's an exam question on this. And so since that's the case, then our efficiency can also be written just in terms of the temperatures, right? So 1 minus TL over TH. In this particular example, the hot and cold temperatures are, the exhaust temperature is 230 degrees Celsius. And we don't know what this is. But the efficiency in this example is given as 28%. So before we go too far, we have to recognize that these temperatures are in degrees Kelvin. It should be. And that's what I said before. The only way you can get 100% efficiency is if this is 0, absolute 0. Great, so we're going to have to add 273 degrees here in order to get into degrees Kelvin. So that's 503 K. And now 0.28 equals 1 minus 503 over mystery temperature, TH. So we can subtract this from 1, then that means that 503 over TH has to equal 0.72. 28% efficient means 72% wasteful. Super. And then we divide 503 by 0.72, and that's how we get a larger number. But there's something I like about this question, and I'll show you in a second. So this would be 699 Kelvin. And I could subtract out 273 to get it back to degrees Celsius. And so that's 426. So one of the takeaways from this is that in this particular cycle, If I can get a bigger difference between TL and TH, then I'll improve the efficiency. And that's how come we have smokestacks, right? So let me just do like a generic little factory down here. Here's our little factory, sweatshop, and there's a big old fire going on. Those are flames. Oh, wait. Is that the orange? Oh, yeah. Yeah, there's definitely a fire in there now. So this is our QH. And if we have a smokestack, it goes up here, that's where our QL lives. So the higher the smokestack, the more cooling can happen. And that's going to lower TL. Now I'm writing these side by side. Remember, heat is the flow of energy, and temperatures happen to be where the action's happening. So taller smokestacks, lower TL. Taller equals a lower TL. And if that's lower, then that equals efficiency going up. So there's a little interesting side note. All right, I'm just going to pause for a second if you wanted to do a quick screenshot of that, if you're doing okay with that. And then I wanted to do one last example that involves power, just so you can see what that looks like.
Can you explain to me why the efficiency goes up? I guess I'm confused by that part.
Yeah, it's so if we focus right here, Marianne. Right, so the TH isn't going to change. And if this gets lower, then this is a smaller number. In this particular example, this cycle was 28% efficient, but 72% inefficient. And so if this number was smaller, then the inefficiency would go down, so the efficiency would go up. Does that help?
Yeah, is that like a true representation of how efficient the system is? Because, I mean, I'm viewing it as like a taller smokestack, but the heat, like the temperature could be, or heat could be, it could heat up the smokestack, so you're losing, I don't know. I'll think about this more.
Yeah. Well, also, I mean, there's something else happening in here, right? Which is the work, right? So if there's a bigger difference between these two, then the concept says that if there's a bigger difference, then the difference between those is going into whatever useful work is happening.
Like if there's a turbine that's spinning, because I was having the same thought. So if there's a turbine that spins when there's a heat difference, if the heat difference gets smaller, the turbine spins slower. Is that the idea?
Yeah, that's exactly it.
Okay.
And there's also an interesting thing too that happens because of that. Like some people like to keep freezers outside, like in their garages or something like that. If they have like a garage attached to the house, and keep a freezer out there just because it's rid of the noise. But in the wintertime, the temperature difference is actually lower and the efficiency of the freezer drops tremendously. So it's actually a big waste of electricity to keep a freezer in a cold place. You might not cycle on as often, but when it does cycle, it's going to be very inefficient. Okay, cool. So let's do one more example, and I'll throw out any more questions about this one. I think, again, if you just keep this diagram in mind and focus on harvest, use, waste, then it makes the efficiency calculations easier to do. And the ones that involve temperature are only true for if it says Carnot cycle, because the heat is happening on isotherms. All right, so one more and we'll take a look at some power applications. And power applications are closer to being the truth because, you know, in most practices, it's not a one and done, it's a continuous cycle. Okay, let's see, great. So in this one, this is 24 out of the questions that are loaded onto Canvas. And it talks about two temperatures, so 210 degrees Celsius, so TH equals 210 degrees Celsius, so we're going to have to convert that into degrees Kelvin, and TL is 45 degrees. And it is a Carnot cycle. And engines power output is 950 watts. And we're supposed to find the rate of heat output. There's a quiz question related to this. So this is a good example for us to do. Okay, well, let's go ahead and do the efficiency part really quick. So we're going to add 273 to both these numbers. So plus 273 plus 273. And then our efficiency is going to be equal to 1 minus TL over TH. So that's equal to 1 minus TL, it's 45 plus 273. So that's 318. And then 210 plus 273 is 483. And so our efficiency is going to come out to 34%. Or as a fraction, 0.34. Okay, well, let's do that diagram again. Boy, Joe loves that diagram. So we have hot stuff coming in, Q, H coming in, like that. We suck off work, and we ditch the energy that is left over. Now it says the engine's power output is 950 watts. So that's what this is. That's the useful work that we get out of it. Now this was typically in our opening, we refer to this as energy, right? So joules. But since this engine is on continuously, it's more practical to talk about its power output. Joules per second. And then what we want to do is find the rate of heat output, which is how much we're wasting. That's this number right here. So this is heat input. This is the work output. And then this is the heat output, or wasted. Now, interesting thing, so in the wintertime, if you have an internal combustion engine, then this heat is not necessarily all wasted. Some of it can be used to actually warm your car. So there's a heat exchanger, which takes heat and drives it into the passenger compartment. And it's very closely linked to, there are actually two different sources of cooling that are happening. So when you turn your heat on, you're actually trying to help cool your engine off. And then the radiator doesn't have to work as hard. Unfortunately, with older cars, when they develop a problem with the head gasket, then those mixtures of coolant start getting mixed together and you wind up with antifreeze spitting into your car. That was me all last winter, trying to squeeze year 19 out of our Toyota Camry. All right, we're almost there, so let's see what we can do with this efficiency. So we also know that E is equal to work over QH, and we know that QL is going to be what's left over. So that's QH minus QL is equal to work done. So we can use this efficiency to find out what QH is if W is 950. So 0.34 is equal to 950 over QH. So then I can find out what QH is. Multiply both sides by QH, divide both sides by 0.34, so 950 divided by 0.34. And so that's 2,794. Minus QL is equal to the work done, which is 950. So we add this to both sides and subtract 950 from both sides. And that's 1844. And that's watts. Yeah, I mean, it's only 33% efficient, so the amount of heat wasted is twice as much as the actual energy that we got to do useful work. Yeah, that's the way it goes. Centuries of burning stuff. Got to stop. One of the comments is that, you know, if, let's suppose you have an electric vehicle and you're still relying on a gas-fired power plant to make the electricity to charge your electric vehicle. So how is that any better than you know, just putting gas into your car? And the answer is that the efficiency of the power plant is definitely going to be more better than the efficiency of your car. So it still is a good thing. Now here in Vermont, we're pretty close to not relying on any gas power plants, which is a really good thing. but we're a blip on the national grid. The amount of energy used in Vermont is just a tiny, tiny sliver. However, the good news is I think California has legislation committing to be carbon neutral by 2040. It might even be sooner than that. And that's awesome because California is approximately, I think that's like the 8th largest economy in the world. So yeah, I mean, I think there's definitely reason for optimism as long as we keep trying to do the right thing. And you young people out there, vote. So, all right, so that's all the new stuff for tonight. Do you have any questions? Okay, go ahead.
Oh, this is kind of it. This isn't. If anyone has a more on-topic question, I have a question about superchargers and diesel engines and if it's possible. If it just relies on the compression of the gas, or if that would throw off the timing if you put a supercharger on a diesel engine.
It's still possible for a diesel engine to be have electronic fuel injection.
But then there's no spark to ignite the fuel, so wouldn't increasing the pressure make it explode too early in the cylinder?
Yeah, I can imagine so. But if you were able, yeah, I don't know.
Okay, this is an unknown. All right.
Yeah, I mean, maybe that was a claim by Volkswagen when they were lying about their fuel efficiency. That's a funny story. Not really, but. Okay, anything else? All right, so we talked about what Tuesday's going to look like, right? There's no lab due. You're not going to show up with a lab due. And we're not going to do the chapter 15 assessment, the quiz for this material. We're not going to do that on Tuesday night. That's still going to be online. So I might open it, maybe this weekend I'll open it. And then so you can get in, and if you have any questions on it, it would be great for you to bring questions about it. You can certainly do that for the first couple of minutes of our face-to-face time. Okay, good. All right, well, if there is anything you want to, chat about within a smaller group, you can stick around. But otherwise, I'm done. So if you want to exit the room, you're welcome to. Thanks. Have a nice weekend.
Thank you. You too.
Thank you.
Thank you. Thank you.